In the previous lecture, we had met formally for the first time tensors of higher rank. We had taken outer products of vectors and covectors, and by modeling things on how these outer products transform, we had figured out transformation rules for these higher rank tensors. What we had ended up with is basically a definition which goes like this. A tensor of rank p, q is an object which can be described by a total of n to the power p plus q components, where n is a dimensionality of your space, and under a coordinate transformation in which the coordinates, the n coordinates describing your system, changes from xi to x prime I given by some function x prime I of x1, x2 up to xn. These components transform according to the following rule. So first of all, you write the components with p upstairs indices I1, I2 up to IP, and q downstairs indices, and the transformation rule which tells you how to find out the I1, I2 ... IP J1, J2 ... JQ component of T in the new coordinate frame is simply this. For each of the upper indices, you pick up a term which is a vector transformation term, del x prime I1, del x K1, then you have del x prime I2, del x K2, so on, del x prime IP, del x KP, that's the last of the lot. So P vector transformation coefficients, and in addition you have Q covector transformation coefficients, del x prime J1, del x prime J1 of XL1, del x L2, del x prime J2, and so on all the way down the line till you get to del x prime LQ, del XLQ, this is a covector transformation coefficient, remember, del x prime JQ. These are the factors which multiply T, K1, K2, KP, L1, L2, LQ. Of course, there's still a summation over all the K's and all the L's to be done, but this is how you find out the new transformed components in terms of the old components. And this is how the old phases definition of a p, q tensor goes. It is a bunch of n to the p plus q components which transform according to this particular rule under a coordinate transformation. In addition to this, let me stress that sometimes we do say that tensors transform according to this rule, but that is a bit of an abuse of language. It's not really the tensor which transforms. It is the components which describe the tensor which transform when you go from one coordinate system to another. But this particular abuse of language is very, very common. I might have definitely lapsed into it several times in the previous lectures, and I cannot guarantee that I will not use that wrong language in the future. But let me just stress once again, in the definition of the tensor, it is the components of the tensor which transform when you actually go from one frame to another. The tensor as an object, of course, stays the same. It's something which exists beyond the coordinate system, as we will discuss in today's lecture. Before we go on to the main topic of today's lecture, which is essentially talking about tensors without having to invoke coordinates and hence components and their transformations all the time, let me just say one thing more about a kind of transformation of coordinates that is very common, which is a linear coordinate transformation. Let me just remind you that under a linear coordinate transformation, where xi goes over to x prime I, given by Sij xj, here the s upper I lower j are coefficients of a transformation which are fixed quantities. Here it is easy to see that del x prime I, del xj, the transformation coefficients for vectors are nothing but Sik themselves. And on the other hand, del x prime I of xj, the covector transformation coefficients, turn out to be denoted by s lower I upper j. And these, let me remind you once again, are nothing but ijth elements of the matrix S transpose inverse, where S, of course, is a matrix composed out of these elements, Sik. Now, under such a coordinate transformation, the rule which governs the way in which components of tensor transforms is straightforward. All you do is write T prime I1, I2, IP, J1, J2, JQ. The new component, or the component in the new coordinate system, is simply Si1, K1, Si2, K2. That is one vector transformation coefficient for each upper index. These are, of course, nothing but del x prime I1, del x K1, del x prime I2, del x K2, and so on. But these are what they translate to for general linear transformations, as opposed to general coordinate transformations, which could even be non-linear. These are for the upper indices. For the lower indices, you have covector transformation coefficients, Sj1L1, Sj2L2, Sjp-Lp, JQ-LQ, because that's the number. Q is the number of lower indices. All this multiplying T, K1, K2, Kp, L1, L2, Lq. By now you may have gotten pretty bored seeing the same thing being written down over and over again. However, this is going to be so important in many calculations that it's actually very useful to keep on repeating this so that you get fully acquainted with this. At the same time, what I am going to say next essentially is going to tell you that you don't really have to mug up these things at all. A better definition of a tensor would actually make these things come out automatically from the definition itself, rather than these being part and parcel of the way you define a tensor. We will turn to that next. If you remember what I said near the end of the very first lecture of the series, you would realize that I find this kind of definition of a tensor somewhat unsatisfactory. Let me just remind you why this is unsatisfactory. What you are really talking about is an object which exists out there in the physical world, which is being described by a bunch of components simply because you have chosen a specific coordinate system. Now, since the coordinate system choice is arbitrary, as long as the components have enough information to pinpoint what the actual object is, we should be able to tell what the new components will become if you were to change your coordinate system. That is why transformation rules exist. But you should realize, as I've said before, the fact that transformation laws exist is an indication that coordinate systems, after all, are artificial, and the real object exists beyond the coordinate system. So can't we talk about tensors without imposing this kind of a transformation rule on them? If the only possible way to define a tensor would be a bunch of n to the power p plus q components which transforms in a very particular manner when you transform your coordinates, then it seems that the coordinate system is intricately tied down to even the definition of a tensor. You are trying to define something which exists beyond the coordinate system by essentially saying what happens to the components when you change the coordinate system. Now, as I said before, this is, at least at a philosophical level, rather unsatisfactory. I'm not saying that this is wrong, not even that this is not useful. In fact, this is very, very useful. If you want to use tensors in actual physics calculations, you will have to understand and be able to use this kind of definition. However, it would be much more aesthetically pleasing if we could talk of tensors without the transformation rules, and we could define a tensor as an object which exists out there without having to specifically refer to coordinate system. That is what we are going to try to do now, and it will turn out that this actually makes the definition much simpler and much more natural. Remember, we have said that we can define a vector using differential geometry concepts where we do not have to involve coordinates directly into the definition. And once we do that, this coordinate transformation version of the definition would actually follow as a natural property of that object. Now, because we are not using differential geometric notions here, at least not in a big way, we are trying to keep this series of lectures elementary after all, we cannot really do that. So, we are using the definition of a vector as a bunch of numbers, or an object which can be described by a bunch of numbers which transform exactly the same way coordinates, or rather coordinate differentials do when you change coordinates. Let me remind you though that the covector transformation equation was something which we actually derived from a very basic demand. Of course, what we did was take a look at a very specific covector, the gradient of a scalar, figure out how that transformed under coordinate transformations using basic partial differential calculus. And from that, we figured out that there is a new kind of object, something which is described by n components, but at the same time, something which is not a vector because it transforms differently under coordinate transformations. And then what we did was essentially define a covector as any object with n components which transform under the coordinate transformations the same way gradients do. But if you look at the original definition of what a covector is, you would realize that we could have started just from that definition and figured out the same transformation equation. Let me show you how. But first, let me remind you that a vector being described just by its components is only part of the story. Frankly, the vector v is not just its components, is basically something like this: v1 e1 plus v2 e2 plus v3 e3 and so on, all the way up to vn en. What this means is that we are using a bunch of basic vectors, a specific n tuple of them, taken in a very specific order, to form what is called an ordered basis of the vector space formed by all vectors, and any vector can be expanded in terms of that, where v1, v2, v3 up to vn are just n real numbers, the so-called components. And let me also remind you that this relation actually tells us that in a way the components transform under a coordinate transformation in exactly the opposite way in which the basis does, and as a result the object v, which is something out there independent of the coordinate system, does not really change when you change your coordinate system. In other words, the transformation laws really go like this. Under a coordinate transformation, the fact that Vi is transformed in this manner can really be figured out as a consequence of the fact that the EIs, the basis vectors, they transform like this. Let me just show you how this works out in practice. The transformed components seen as coefficients of the transformed basis vectors gives you V prime I, E prime I, which is a vector described in the new basis. But what is V prime I? It's Sik Vk, and E prime I is Sij Ej. Note that we have to keep dummy indices separate. We do not want to mix up two different dummy indices. And that's okay here because I've used K and J as two different dummy indices. This I has to be the same as this I because you do imply a contraction or a summation here. This rather obviously is equal to this expression. And as we had shown earlier, Sik, S lower I upper j, is actually the jkth element of the matrix S inverse or the identity matrix. And that's given by delta jk. So delta jk vk ej. And this ensures that the transformed vector is actually equal to vj ej. So the vector itself does not change as we have been stating. So the origin of the covector transformation rule is really even more basic than the way in which a gradient transforms. This basically tells you what are the coefficients that you need to combine the old basis vectors to get new basis vectors. And let me remind you once again that we had already talked about this. As far as nomenclature is concerned, covectors used to be called covariant vectors, vectors which transform in the same manner. But what was really meant is covariant vectors are components which transform the same way the basis vectors do. And what we are calling vectors used to be called contravariant vectors because they transform, or rather their components transform, in a way opposite to the way in which basis vectors do. So the nomenclature contravariant and covariant, which is really out of fashion nowadays, but still prevalent in some textbooks, actually comes from comparing the transformation laws with those of the basis vectors. How will this help us figure out the way in which covector components transform? Let me quickly remind you that we essentially wrote a covector, omega, in terms of its components, which we wrote with lower indices, omega I, and the idea essentially was that when a covector acts on a vector to yield a scalar, you would write it like this, and this will be a scalar quantity, something which does not change when you change your coordinate system. And in order to do this, and this happened basically because the covector transformation rule went something like this, omega prime I equals Sik omega k. Now, let me justify this particular transformation rule starting from the definition of what a covector is. But in order to do that, we have to define a covector properly first. Of course, we have already defined a covector as an entity which is described by n components which transform in a particular manner under a coordinate transformation. But let me try to give you a definition of a covector without involving components at all. But that is something we have already done before. A covector is nothing else but what is called a dual vector in linear algebra. It actually is a map which acts on a vector space V to produce an element which is a real number. So it's basically a map from V to R, but more importantly, It's not just any map which maps a vector into a number. It has to be a linear map from vectors to numbers. In other words, if you feed a covector omega a vector v1, let's say the result comes out to be x1, and when you feed it v2, the result comes out to be x2, then when you feed c1 v1 plus c2 v2 to the covector omega, the output should be c1 x1 plus c2 x2, the same linear combination of the outputs as of the inputs which went in. So first of all, how does this help us define components for a covector? And then how does it help us figure out how that will transform? The answer is pretty straightforward. First of all, I want to figure out what omega does to a vector v. But we have already seen just now that you can write a vector v in terms of the vector components and the basis vectors like this. Now remember, a covector is a linear map, and what you are putting in here is a linear combination. A linear combination of the vectors e1, e2, e3, en multiplied by numbers v1, v2, v3, vn. So, because of the linearity of the map, this result is the same as v1 times omega e1 plus v2 times omega e2 plus all the way up to vn times omega en, or vi times omega acting on ei for short. Now this quantity, omega acting on the ith basis vector, this is just a number, and we define this to be the ith component of my covector omega. So I get one number omega I for each value of I running from 1, 2 all the way up to n. And this is perfectly consistent with our earlier definition of covector components, because once we have put in this definition, what we get is omega acting on V has to be nothing but Vi times omega acting on Ei, and omega acting on Ei is just omega I. And this is exactly what we have said earlier is the result of a covector acting on a vector. It's a contraction omega I Vi, and the upstairs downstairs index positioning ensures that after summation you end up with a scalar. Okay, so now we have managed to define the ith component of a covector in a natural fashion. It's just nothing but what omega does to the ith basis vector. But how does this help us to figure out what the transformation rule will be? The answer is simple. When you transform your coordinates, your basis vectors change. The omega, the covector, actually stays the same object no matter which coordinate system you use, but your basis vectors in your original vector space change, which is why vector components changed. And now you are going to use this to figure out how this change in the basis vectors will cause a change in the components of omega. Well, what is the ith component of omega? It's nothing but omega acting on Ei. In your new coordinate system, you will have a new basis. And omega acting on E prime I will simply be the ith component of the same covector omega in the new basis, or after you change coordinates. So omega prime I is nothing but omega acting on E prime I, and omega acting on E prime I is simply omega acting on Sik Ek. That exactly is how basis vectors change. And this simply tells you that the new omega prime I has to be Sik. Sik are just numbers, so they can come out of this linear map, times omega acting on Ek. And omega acting on Ek after all is omega k. So you end up with Sik omega k. which is nothing but the transformation rule for covector components. What I want to emphasize here is you did not have to define the transformation rule for the components of a covector independently. The moment you defined a covector as a map which acts linearly on vectors to produce numbers, the transformation rule for covector components followed automatically. We will now go on and use the metric tensor to show that something very similar happens there as well. Instead of thinking of the metric tensor as a bunch of n-square components, you start thinking of this as a map which takes in vectors and produces numbers. The definition of the components and the definition of how the components change when you carry out a coordinate transformation follow rather trivially from it. So that is what we are going to try to see next. Now, when we met the metric tensor in the previous lecture, we actually met it through its components. What we did was say that if you had an inner product defined on your space which had some kind of weighted sum of the components ai, bj, weighted in this case by numbers which we call gij, and this turned out to be a scalar, then gij would have to have a particular kind of transformation rule. In fact, what we showed is something which we have already mentioned in today's lecture. G prime ij would have to be something like Sik Sjl Gkl. That would be the transformation rule. Now let us try to see how we can first of all define the metric tensor without referring to its n-square components to begin with. And once we have defined this object, the metric tensor, in a coordinate independent way, how that definition will lead us to its components, and from there to the component transformation rule. It actually is a pretty straightforward thing, simply because the role that the metric tensor's components play here is the following. Given two vectors, A with components A upper I and B with components B upper j, it allows us to produce a scalar. So, in a sense, G is simply a map which takes two vectors and produces a number. So, G is simply a map from V cross V, the Cartesian product of the vector space with itself, to R. That's just a fancy way of saying G takes a pair of vectors and produces a real number. Now, not only that, it produces this real number in a multilinear fashion. So, this is an extension of what we saw for the covector. A covector is a linear map which maps vectors into numbers. The metric tensor here actually maps a pair of vectors multilinearly into numbers. So what does this word multilinear mean? It simply means this. If we keep one of the vectors fixed and replace the other one by a linear combination, where of course the notation should make it obvious that we are implying here that B1 and B2 are two vectors and C1, C2 are just two numbers, then the result will simply be C1 G of A, B1 plus C2 G of A, B2. So this part of the definition by itself would say that this map is linear in the second argument, or here the second vector. But multilinearity simply means that this works for all the arguments, in this case for the first argument as well. So if we were to keep B fixed and replace A by C1, A1 plus C2, A2, once again A1, A2 are two vectors and C1 and C2 are two numbers, then you will again get C1 G A1, B plus C2 G A2, B. linear in both the factors, or in general a multilinear map would be linear in all its arguments. So now let us take a look at what such a multilinear map would do to two arbitrary vectors which have been expressed in terms of their components. Remember, we can write the vector A in terms of AI, EI, and vector B in terms of the same set of basis vectors as BI, EI. So what does G do to A comma B in terms of these components AI and BI? That, of course, is simply G acting on AI, EI. And once again, let me remind you that you cannot mix up dummy indices. So the dummy indices for B should be changed from I to something else. What exactly does not matter. But for the time being, let's just say BJ, EJ. Now, because this map is linear in the first factor, the coefficients AI can simply move out and you're left with G acting on the basis vector EI, and the second argument, of course, is B. So BJ, EJ. But now you can use the multilinearity in the second factor and pull the BJs also out. Once again, let me stress that the components AIs and BJs are just numbers, so they can move out of the multilinear map. And if you compare this with what we did for the covector case, it should be obvious that the map G is completely determined if you tell me what G does to the basis vector pair EI, EJ for all pairs. And so this particular quantity essentially tells you what the map does, or not really this particular single quantity, but all such numbers which come from using all possible pairs of EI and EJ. And this is exactly what we are going to call the ijth component of the metric tensor. So, by definition, Gij will be G, the map, acting upon or being fed the two basis vectors EI and EJ. And once we have done that, we can simply rewrite G acting on A and B in our familiar inner product form, the form that we saw in the last lecture, Gij, AI, BJ. So this is exactly how we can define the components of G just from the object G independent of the coordinate system. The components, of course, depend on the particular coordinate system chosen because the basis vectors EI and EJ essentially come from the particular coordinate system. Having traveled this far, figuring out the transformation law for components essentially becomes very, very simple. When you carry out a coordinate transformation, the basis vectors, of course, change to EI prime being equal to SIK EK, as we have been seeing several times now, and the new components in terms of the new basis vector G prime Ij will be nothing but G, the object, which, let me remind you once again, is independent of the coordinate system, acting on the new basis vectors E prime I and E prime J. So, all you have to do is write E prime I and E prime J in terms of the old basis vectors. So, write E prime I as SIKEK, write E prime J as SJLEL. Once again, as always, taking care not to mix up two dummy indices. And then use the fact that SIK and SJL are numbers so that they can be pulled out. In the previous derivation, we were careful. We pulled them out one by one, but it should sort of make it should be obvious that you can actually pull them out together, and you can get SIK SIL G EK-EL. And just recognizing the fact that G acting on EK-EL is simply nothing but GKL, the old components, the coordinate transformation rule for the metric tensor simply becomes SIK SJL GKL. Thus, we see that the transformation rule for the components of the metric tensor follows naturally from the fact that the metric tensor maps two vectors linearly into a scalar. In order to figure out what would happen under a general coordinate transformation, all you really need to do is remember this translation rule that what is S lower I upper K for a general linear transformation transforms to del x prime lower I del x k in the case of a general linear transformation. You can actually start with a basis starting from the coordinates in a differential geometric language, and there you can strictly justify why this S lower I upper K has to become this for a general coordinate transformation. But because we are avoiding going full differential geometric on this, we will not try to justify this. We will just say that this is how you translate one coefficient in another. So, for a general coordinate transformation, our component transformation rule for the metric tensor simply becomes G prime ij del x k del x prime I del x l del x prime j GKL, which is of course the familiar transformation rule that we have talked about in a previous lecture as well. Now let me point out that while mapping two vectors multilinearly into a scalar was a natural thing for the metric tensor to do, basically because that scalar is nothing but the inner product, we can keep on talking about maps other than the metric tensor which maps two vectors into a number, again in a multilinear fashion. Now, if we do that, we can of course write the action of this map T on the vectors AB in terms of the components AI, EI and BJ, EJ, and just by following the argument that we had given a while ago, this simply becomes AI BJ times T acting on EI, EJ. And just like we did for the metric tensor, we can call this quantity the ijth component of the tensor T. And now we are saying that the map T acting on A and B leads to the number T lower ij ai bj. Of course, the numbers Tij contain complete information about this map, because once you know them, you know exactly what this map is going to do to any two vectors. So, these are the components which describe the system completely. Again, following along the lines of the metric tensor, if we want to find out what happens to the coefficients Tij or components Tij under the coordinate transformation, all we have to do is figure out what T does when it acts on E prime I and E prime j. This of course will be T prime ij, or the ijth component of T in the new frame. And just by using the fact that E prime I is Sik Ek and E prime j is Sjl El, both these being the same coefficients as for covectors, we immediately see that for any tensor which maps two vectors into a number must have this transformation rule, which is of course our familiar transformation rule for all 0, 2 tensors. So what are 0, 2 tensors in this new language? They're nothing but multilinear maps which map two vectors into a number. Well, then what would 2, 0 tensors be? A hint can be easily found from what a 1, 0 tensor is. A 1, 0 tensor is of course nothing but our old friend, a vector. Can we think of a vector as a linear map? It seems rather strange to think of a vector as a map, but if you just give it a bit of thought, you would realize that we say that omega, a covector acting on a vector, produces a number. Can we just turn this around and say that this actually is nothing but a vector acting on a covector to produce the same number? In other words, if we were to define the action of a vector on a covector as simply a number which is exactly equal to what the covector gives acting on the vector, if this were just the definition of A acting on omega, would that define a linear map? The answer is yes, but before we go there, we need to be able to define addition of covectors first, because without that, it's impossible to even talk about linearity or otherwise of A when it's acting on a covector. Now, how do we define the addition of covectors? Can it at all be defined in the first place? Well, the name covectors has the word vector in it, and that's a big hint that actually they form a vector space of their own, which does mean that there should be a way of defining their addition. In fact, those of you who have done a course on linear algebra, for them this will be old stuff. You would know that the bunch of all linear maps acting on a vector space actually forms a vector space on its own called the dual vector space V star. So if V is your original vector space, V star is actually a space formed by set of all covectors, and on such a set you have to define the addition of two covectors, and this is done by the most natural way possible. You define the sum omega 1 plus omega 2 as a covector which acting on a vector A produces exactly omega 1a plus omega 2a. This seems so natural that it hardly seems worth even specifying this as a definition, but a bit of thought will show you that this is actually nothing but a definition of what you mean when you add two covectors. Similarly, multiplying a covector omega by a number alpha leads to another covector which by definition acts on A to produce the number alpha times the number omega A. Note that on the right hand side of both of these definitions, the plus and the into are really being done between real numbers. So this is a perfectly well defined option. You should be able to check that under these definitions of addition and multiplication by a scalar, the set V star really becomes a vector space on its own, which means this obeys all the basic conditions for a vector space. This again, as I said, would be old stuff for all of you who have done a linear algebra course, but if you haven't, you should actually check this out on your own. Being armed by this definition of addition of two covectors, let us check whether we can think of a vector as a linear map when it acts on a linear combination of two covectors. Now, by our definition of this object, this is nothing but the covector alpha 1 omega 1 plus alpha 2 omega 2 acting on the vector A. This of course is a number, and as we have already defined just now, this is nothing but alpha 1 times omega 1 acting on A plus alpha 2 times omega 2 acting on A. And now let's turn this around once again. Omega 1 acting on A is nothing but our new definition of a vector acting on a covector. And similarly, omega 2 acting on A is nothing but A acting on omega 2. And now you notice that what we are saying here is A acts on a linear combination alpha 1 omega 1 plus alpha 2 omega 2 to produce a linear combination of the results alpha 1 times A acting on omega 1 plus alpha 2 times A acting on omega 2. So just like a covector can be thought of as a linear map acting on vectors, in fact that is how covectors are defined in the first place, a vector is a linear map that acts on covectors. Now it should be pretty easy to understand what a 2, 0 tensor will be in this language. It will simply be a map P which takes in two covectors and maps them onto a number in a multilinear fashion. So this has to be multilinear in the sense that it's linear in both the covectors omega 1 and omega 2. I put brackets around the 1 and 2 here just to sort of stress that these are two different covectors and these 1 and 2 does not indicate components. Well, from here, jumping onto a mixed tensor, say 1, 1 tensor, it's pretty straightforward. A 1, 1 tensor Q would simply be one which takes one covector omega and a vector A and gives you back a number, again in a multilinear fashion. If you replace the covector by a linear combination, the result would become a linear combination. If keeping omega fixed, you had replaced the A by a linear combination, the result would again be a linear combination. Well, from here going on to a PQ tensor is pretty straightforward. All a PQ tensor would ever be is a multilinear map with P plus Q arguments, of which the first P arguments are P covectors and the next Q arguments are Q vectors. So this is just what a tensor is. It's a multilinear map which maps covectors and vectors onto a number. So you can think of a tensor really like a machine which eats up covectors and vectors and turns out numbers. The only real restriction here is that it does so in a multilinear fashion. If you keep all its arguments but one fixed and replace that one by a linear combination, the resulting answer would become a linear combination for the two individual cases. Okay, so now we have defined the general tensor as a multilinear map. Short and sweet. No transformation rules, no components. It's just something which maps a bunch of vectors and covectors into numbers. But now we want to translate this back into the language of components and see how the component transformation rule that we had written down in earlier lectures and also in the beginning of this particular lecture follow from the definition itself. Before we go there, we need to do one more thing. We have already established that covectors form a vector space. What we need to do is figure out a suitable basis for that vector space. Because remember, components of tensors, in the case of the metric tensor or the 0, 2 tensor, came out of the basis space for vectors. Now that our tensors eat up covectors as well as vectors, we will need basis vectors for both of them in order to talk about components. And then the question would simply boil down to how do those basis vectors for covectors change. We already know how basis vectors for vectors change. And that is all you will need to know to figure out the transformation rule for tensor components. So let us turn to that next. The task at hand then is to figure out a suitable basis for the covectors and then of course figuring out how these basis vectors transform when you carry out a change of coordinates. Now, we will go about the task of finding a suitable basis in a way which is slightly opposite the standard way in which things are done. Usually you establish a basis first, and once you have got a basis, you can talk about components in terms of them. However, as we have already seen, for a covector omega, the components omega I can be easily figured out to be omega acting on ei. So what we want here is to be able to express the covector omega like this: omega I times the ith basis vector for covectors. Let's call that alpha I. That is, I want to write down any covector in the form omega 1 alpha 1 plus omega 2 alpha 2 plus omega 3 alpha 3 and so on up to omega n alpha n. After all, there are exactly n components or n coefficients that we have figured out for omega, and we will need n basis vectors to go with that. So, under what conditions would this really be correct? Would omega be something which you can write as omega I alpha I? Well, all you need to do is to fall back on this result that omega I is nothing but omega acting on the ith basis vector of the original vector space. So using that, what we get is omega I is omega, which is omega j alpha j in our definition here, acting on the ith basis vector ei. Remember here, ei is the ith basis vector for the vector space underlying the whole thing, and alpha j is a jth covector basis. And needless to say, I have used an upstairs index to denote the jth basis vector simply in order to keep the upstairs downstairs convention for summation intact. Now here, the result obviously is rather trivial. This sum has to be omega I. So this tells us that in order that this happens, no matter which omega you choose, which set of omegas you choose, you must have alpha j acting on ei give you a number which picks out only omega I from this sum, and that's only possible if this is delta ji. So our set of basis vectors for covectors is defined simply by this relation, which is often called the duality relation. And in case any of you find this particular relation reminiscent of reciprocal basis vectors that you studied perhaps in solid state physics, it is really not an accident. In fact, the reciprocal basis vectors in condensed matter physics should perhaps better be described in terms of covectors rather than vectors, although conventionally they are always expressed in the language of vectors. Now, just to summarize, our basis vectors for the covector space would be something like this. Alpha 1 would be a linear map, a covector which acting on E1 gives you 1, acting on E2 gives you 0, in fact gives you 0 acting on every other E. So, other EI. So, alpha 1 En is 0. Similarly, alpha 2 acting on E1 gives you 0. Alpha 2 acting on E2 gives you 1. And so on and so forth. It should be easy to see that finally we end up with alpha n acting on En giving you 1. And this completes a full description of what these basis covectors are. Now we come to the question about how do these basis covectors transform when you change your coordinate system. One easy way to answer that would be to simply demand that omegas, the omega, the covector, does not change under a coordinate change, coordinate transformation. Once again, let me remind you that although we have been talking about these kind of objects, vectors, covectors, etc., in terms of how their components change when you change the coordinates, the objects themselves are independent of coordinates, they don't change. It's just the components with respect to some coordinate system which change when you change the coordinate system. But if omega does not change, then we must have omega lower I alpha I equals omega prime I alpha prime I. This is just nothing but the statement that the covector omega is the same in both the frames. It's only the coordinates, only the components which change. Now we know that omega prime I is related to the older covector components simply by this relation. And this will be enough to tell us how alpha I and alpha prime I are related. So all you really need here is to note that omega I alpha I is equal to Sik omega k alpha prime I, which can of course be rewritten trivially in this form. Note that this equation is going to be correct no matter what omega you take. So in particular, what you can always do is look at this as an equation in which the coefficients of like omegas must be the same. In other words, here omega k has a coefficient given by S lower I k alpha prime I. On this side, omega k has a coefficient alpha k. Let me remind you once again, this I is just a dummy, so you are fully within your rights to change it to anything that suits you. In this case, change it to k. So, because this is valid for all k, you immediately get the relationship alpha k has to be equal to Sik alpha prime I. So what we have managed to do is relate covector basis to the transform covector basis. The only problem is, what we have got is a formula which gives us the old covector basis in terms of the new ones, whereas what we actually need are the alpha primes in terms of the alphas. Now that is actually pretty easy to get to by simply using the fact that Sik and Sjk are elements of S transpose inverse and S respectively, and this immediately leads us to the result that this is delta Ji. Now how do we use this? This is rather trivial, but this is also pretty important. So let me just explain this in some detail, perhaps unnecessary detail. If you want to get rid of the S from this side and move it to the other side, what you need to do is multiply by or contract it with the other kind of S, which will cancel this by bringing in a delta. That much should be obvious. But what is important is what I have here is Sik alpha prime I. Here the I is a dummy index, so that cannot be touched any further. So if I want to contract it with something, I should contract it with this k. So this S should have a downstairs index k and an upstairs index which is free. So I just put that as J. Now, of course, if you do this, you have to do it on the other side as well. So we get Sjk alpha k equals this expression. But now, this thing, according to the result that I just wrote down, is actually delta Ji. And thus, what we have is alpha prime j on the right hand side. So, we have found an expression for alpha prime in terms of the alpha. Or if I want to write alpha prime I, all I will have to do is ensure that this free index is I on this side. So what I will get is Si. And the dummy index can be written anything, so I can also write it as J if I want to. So this is the transformation equation that we have for the covector basis elements. Just to check that this is actually consistent with what I know about these basis elements, Let's try out this expression. What should alpha prime I do to E prime j? The answer is straightforward. E prime j is a transformed vector basis and alpha prime a is a transformed covector basis element. So when alpha prime a acts on E prime j, you should get delta ij. But let's check whether that's true. Now alpha prime I, as we have just said, has to be Si k alpha k. The same relation as this one, except that we have been careful enough to change the dummy index from this j. This j is a free index, so I should not confuse the dummy index with that. On the other hand, E prime j has to be Sj L El. So using the fact that a covector, alpha k is after all a covector, is a linear map, I can pull the coefficient Sjl out of this equation and I get Sik Sjl times alpha k acting on El. But this alpha k acting on El, by the definition of the alphas, has to be delta kl. That helps us to get rid of this sum, but at the same time change this L to k. And now using the standard property of these matrix coefficients, this thing is simply delta ij as we demanded. So this transformation rule that we have figured out for the covector basis do work out. Now this should not really come as much of a surprise. Let me just remind you that for a vector v, where you had components vi and basis vectors ei, under a coordinate transformation, the vi transformed to v prime I given by Sik vk, whereas the basis vectors transformed just in the opposite manner, Sij ej, and as a result of that, vi ei, the vector itself, stayed unchanged when you carried out a coordinate transformation. Exactly the same thing happens for a covector. Omega is omega lower I alpha upper I. Omega lower I will transform under a coordinate transformation to omega prime I given by S lower I upper k omega k, and alpha I will transform to alpha prime I, which is Sik alpha k. And that's again just sufficient to ensure that omega I alpha I goes over under a coordinate transformation to omega prime I alpha prime I, which is exactly the same as what it was originally. In other words, just like vectors and their bases transform oppositely, covectors and covector basis transforms oppositely. It just so happens that the covector components transform exactly like the basis vectors do for a vector, and the covector basis transforms exactly like the vector components do. This should not come as much of a surprise at all. But now that we have these results, it should be very easy to figure out how to define components for a general p, q tensor, and on top of that, it should be also very easy to figure out how these components transform. Let us see how this goes about. First, the components. What I want to talk about is, given T as a multilinear map which maps P covectors and Q vectors into a number, how would you define this component I1, I2, IP, J1, J2, JQ? And the answer is very simple. You will take the multilinear map T and feed it P covectors and Q vectors to get this number. But which particular P covectors and Q vectors? The answer is simple. You will feed the I1th basis vector in the first slot, I2th basis vector in the second, so on until you get to the IPth basis vector in the pth slot. These are all covectors. And then you will fill up the Q slots left for vectors with EJ1, EJ2, EJQ. So basically what you do is feed basis covectors to the first P slots and basis vectors to the next Q slots. And this gives us a particular component of the tensor T. To illustrate that these components actually contain all the information that you need about this multilinear map, let us try to figure out what T does to a bunch of P covectors and Q vectors. Let's call them omega 1, omega 2, and so on all the way down to omega P. Then you have the vectors V1, V2, and then VQ. So this is the most general scenario where you are feeding your tensor P covectors and Q vectors. Now, you can write each of these covectors and the vectors in terms of their components using, of course, the basis vectors. So, T of omega 1 becomes omega 1. I call the dummy index here I1. And then you have alpha I1. That's, of course, omega 1. Then you have omega 2, I2, alpha I2, and so on. Omega P, IP, alpha IP. Then you will have V1, J1, EJ1, and so on until you get to VQ, JQ, E, JQ. So, the result, of course, is easy enough to find out. Remember, omega 1, I1, omega 2, I2, etc. All these coefficients are just numbers, and because of the multilinearity of the tensor, they can all be just simply brought out, and you are left with this result. Omega 1, I1, omega 2, I2, all the way up to omega Q, IQ. Then you will have the vector components V1, J1, down to VQ, JQ. All of these are just numbers and they come out. And you are left with T acting on alpha I1, alpha I2, alpha IP, EJ1, EJQ. And this, of course, is nothing other than our familiar T I1, I2 to IP, J1, J2 to JQ. So basically, what we see is that the action of the tensor on any arbitrary bunch of covectors and vectors can be written down entirely in terms of the components of those covectors and vectors with respect to a particular basis, and in terms of the components that you get for the tensor using these bases. So as I said before, the component has complete information about this multilinear map, because once you know the components, you know what this map does to each and every bunch of covectors and vectors. The next question then would be to figure out how these components transform under a coordinate transformation. For this, all we have to do is remember that under a coordinate transformation, the basis vectors for the vector space transforms according to the rule SJK-EK, whereas for the covector basis elements, the transformation rule goes alpha I goes over to Sij alpha j. So different kinds of coefficients. Let me remind you once again. The vector bases transform like the covector components, and the covector bases transform like the vector components. And so under a coordinate transformation, the components of the tensor T changes in the following fashion. To evaluate the new component of the tensor T in the new frame, the I1, I2, IP, J1, J2, JQ component, what you have to do is feed this tensor T. The tensor T remains the same, remember. alpha prime I1, alpha prime I2. So all the new covector basis vectors, alpha prime IP, and then E prime J1 all the way to E prime JQ. But now we know that alpha prime I1 is S I1 K1 alpha K1. Alpha prime I2 is S I2 K2 alpha K2. These are just the new covector basis elements in terms of the old covector basis elements. Finally, you have SIP KP alpha KP. And then is the turn of the vector basis, the new basis vectors in terms of the old basis vectors. This will be SJ1, L1, EL1. Remember, we cannot mix up dummy indices, so because we have called these K's, we have to call these L's. Then we have SJ2, L2, EL2, and so on. Finally, SJQ, LQ, ELQ. The next step would be trivial because all you have to do is use the fact that this is a multilinear map, and hence you can pull out all these coefficients which are just numbers. So we first have a bunch of vector transformation coefficients which actually come from the covector basis SI1 K1, SI2 K2 all the way down to SIP KP. And then you have covector transformation coefficients which come from the vector basis transforming J1, L1, SJ2, L2, SJQ, LQ. This whole thing multiplying T, alpha K1, alpha K2, alpha KP, then E L1, E L2, E LQ. Of course, this quantity here is nothing but the old coefficient T, K1, K2, KP, upper and L1, L2, LQ in the lower indices. So what you end up with is simply this result, that you have a bunch of vector transformation coefficients SI1 K1 to SIP KP. Then you have a bunch of covector transformation coefficients SJ1 L1 to SJQ LQ. Finally, you have T, K1, K2, KP, L1, L2, LQ. This is the familiar transformation rule for P, Q tensors. We had derived this, or at least we had justified this, by looking at the way in which an outer product of P vectors and Q covectors transform. That's what we did in the last class. Here, what we have shown is that once we understand that a tensor is nothing but a multilinear map, this transformation law follows as a simple consequence. Even this picture of a tensor as a multilinear map can lend itself to multiple interpretations. Let me just illustrate this by going back to our old friend, the metric tensor. We said that a metric tensor is a multilinear map which maps two vectors A and B into a particular specific number. Of course, that's written as Gij, Ai, Bj. But that would be the case for any tensor. If instead of G I had some other 0, 2 tensor T, here you would have a Tij, Ai, Bj. But what is important is that this is the inner product of the two vectors of A and B. But ultimately, what G does and what any other 0, 2 tensor does is maps two vectors multilinearly into a number. But let's just imagine. So we can imagine that a tensor is a machine which eats up two vectors and returns a number. The only restriction, as I said, is that this has to do the eating up linearly. However, let's just imagine this scenario. Let's take a fixed vector A and feed that to our metric tensor. The trouble is, the metric tensor actually has 2 slots for inputs, and I've just given A to one of the slots. The other slot is still empty. So what can we interpret this as? What exactly would this thing be? Well, it's easy to see what this is, because of the 2 original slots that G had for inputs, one has been filled up with this fixed vector A, and you still have the scope of fitting in another vector in the other slot. So, this quantity can be thought of as something. Let's call that phi A, in deference to the fact that this will of course depend on which vector A you put in. But this now has a single slot empty. Now what can I feed into that slot? Of course, what I can feed into the slot is a vector. So phi A acting on B will be nothing but G A comma B. So what does phi A do? This maps vectors into numbers, right? It takes the vector B and returns to you the number G A comma B, the inner product of A and B. Fine. But it not only maps a vector into numbers, it's easy to see that it does so linearly. Because if you fed C1B1 plus C2B2, a linear combination, to this particular machine, what you really would be doing is feeding G A in its first slot and C1B1 plus C2B2 on the second. But since G is a multilinear map, it is linear in both the factors. So this will simply be C1 times G, AB1 plus C2 times G, AB2. And if you were to recast everything in the language of our new machine, the phi A, what I get is phi A acting on B1 times C1 plus C2 times phi A acting on B2. So this new machine of ours, which takes only one single vector and produces a number, does so linearly. So this, of course, is nothing but a covector, something which turns a vector linearly into a number. So this is the covector corresponding to A. Does this sound familiar? Of course it should. This phi A is nothing but the object which we have been calling the covector version of the vector A, or what we have been calling A lower I, and we have been talking about lowering of the index using G. This is exactly that, and in the next lecture we are going to explore this and other aspects of this multilinear map behavior of a tensor in some detail. Note that one way of thinking about a 0, 2 tensor would be that it maps pairs of vectors into numbers. Another way would be that it maps vectors into covectors. If you are only interested in rotations and tensors and vectors under rotations, then of course the upstairs downstairs index no longer matters. But then a second rank tensor can be thought of as a way of transforming vectors, pairs of vectors into numbers, or it could just as well be thought of as a way of mapping one vector linearly into another. In fact, that is a meaning which you have already seen before in your elementary physics classes. One of the first tensors that you had met ever, the moment of inertia tensor, was simply a way of mapping angular velocity, a vector, into angular momentum, another vector. Later on, in your electrodynamics classes, you may have met the permittivity tensor, whose job is to map the electric field into the electric displacement vector. In the next lecture, we are going to explore these issues a bit further and also take a look at several applications of this formalism in various aspects of physics. Until then, bye.